world, hackers. How are you doing? This is a next recording in Postgres Hacking 101 on Byte Relay channel. In this book, Terry Pratchett says there is a curse. They say, may you live in interesting times. Indeed, we live in interesting times, and our times are mostly defined by information technologies. What is it? Actually, information technologies is not just fancy iPads or, I don't know, blogs or YouTube or something like that. First, information technology is paper, just paper as a way to store data, to send data, like not email, but a mail is actual information technology, or paper is a way to organize business, to give someone money as a credit, to build your bank, or to organize your I don't know, building company or something like that, to sell stuff. All of this requires information technologies which were for thousands of years built upon paper. And in this sense, databases are paper 2.0. This is the next version of paper. This databases is a new way to organize your business, new way to deal with information technology, new way for information to travel through time, if you know what I mean. And as most usual paper information technologies, these information technologies are organized in pages too. And now we are going to talk about Postgres physical page. What is it? When you configure your Postgres sources, no one is doing this, but you can say with block size and say, for example, 4 kilobytes or 8 kilobytes is the default, or maybe 16 or 32 kilobytes. Let's go with 4 kilobytes. This is uncommon, but that's how it is. Some time it will take to reconfigure my compiled sources. And when it's done, we will push compilation, and let's go to the code to see what it means to have a 4 kilobyte pages. Okay, configuration is done, then make now to see if there are any warnings. It's clean sources, so there should not be warnings. Now let's see. We see this file pgconfig.h, where is the macros block size 400 kilobytes. And this macros is used along all the code. You see there are almost 1,000 of mentions of block size, so it's so widely used. But to operate with this 8 kilobytes, or in our case 4 kilobytes, usually we are using buffer pages. And to observe how typically they are organized, you can go to buffpage.h and see there is a nice pseudographic pic of how these pages residing on blocks are organized. At the beginning, you can see there is a page header, which starts with LSN of a page, and we will talk about it later, maybe in other videos. Then we have so-called array of line pointers, which have offsets of actual tuples, which are stored at the back of a page. Page header typically handle generic information which is used by all access methods. Access method is something to build a relation. Relation might be a table itself or an index to make a quick search through this table. So on the page we have an array of small line pointers. This picture doesn't show us, but typical line pointer, I'd say it's around 16 bytes or so. And tuples. Tuples are typically almost 100 bytes, depending on how wide your table is. And at the end of a page, you can see special space, which contains so-called opaque region, which is designed to be access method specific data. And also at the end of a page, typically there is a checksum to ensure that file system didn't mangle with our data when it was stored. At the same file, buffpage.h, you can find all the API to manipulate with page. You can see that anywhere in a code when you see a type page, it's just a pointer to typically 8 kilobytes of data. Usually it's referred by block number. Block number is 32 bits, which define number of 8 kilobyte segment from the beginning of a relation. And as you can see, any relation can have at most 4 billions of blocks within it. But most interesting part is inside buffpage.h. You can see that there is a generic function. Page is empty, which just is verifying header data, or page is new, which is verifying one of pointers for 0. You see that there are two pointers on the page. Here, PD lower, which is the end of line pointer array, or also called item ID array, and PD upper, which is the beginning of tuples. Tuples are not like stored densely edge to edge. Sometimes they are sparse and there is a space between them, and also there can be some alignment bytes needed between tuples. This API of dealing with pages is like, it was formed by necessity, like something that we need, we add there. I think if you are designing some new access method or hacking some new way of working with data, and if you want to add some new method, it's not like written in stone. It's possible to advance it. But most of the time, there is enough of functions that you would need. And most interesting functions are at the end of a file. Here we go. Page init is initialization of page. Page get free space used every now and then when we need to understand if we can place new tuple on this page. And interesting for me personally is page index tuple override. And there are two versions. Index tuple override and override no compact. Why we have these two versions? Because all access methods are storing tuples on a page differently. Some access methods are sparse and they do not compact tuples when they kill it and remove it from line pointer array. Sometimes some access methods are dense, and when they remove a tuple from a page, they shift all other tuples to the place that was an empty hole. And this is a relatively new functions. We can search through code to find patterns where they are not used. For example, let's take page add item function. This must be somewhere here. It's macros actually for page add item extended. Where is it? Page add item. Yeah, here we go. And search through the code. We see there are 83 results. I found this pattern which can be replaced by index tuple override in many different access methods. For example, If we open Brin, there is one place where we doing delete and then add item. This is the exact place where you can just override the item at this in place. Another is generalized inverse index. Here you can see there is a page index tuple delete and page add item. This is just an override of a tuple. And finally, I found it in spgist. Spgist, where is it? Here, spgist. Yeah, index tuple delete and index and page add item. Let's reuse another function here and see if it is working. See if it is working. Where is it? Where is our function? Page index tuple override. First argument is obviously page. Second argument is offset number of tuple on a page. Here we go. Third is new item. New item here we go. This is it. And the last one, size of a new item. It's here. Looks like that's it, but no. Every time you change something in an index or in a heap table, you need to do it twice. Why twice? Because the same can be repeated during replay, during crash and replay after the crash. Let's go to find. This is a place, SPG add node action. This is a replay of write ahead log, and we have to repeat all the same, but for write ahead logging. There are slightly different arguments, but with all the same meaning. Okay, should work now. Let's try to compile it. Doesn't work. Did I misspell it? Error is on line 276. 276 must be here. Did I save everything? Yes, I did. What's wrong? There must be something wrong. Maybe I changed something in other files. No, I don't see other changes. Yeah, here is no local variable page. That's what was the problem. Now it compiles. And almost certainly it must pass the tests. Let's see. Let's wait while temporary installation will prepare. By the way, this temporary installation is installed all the way near the code in so-called temp install. see here, it sometimes make difficult to work with so many failed tests. Okay, it's difficult to work with configuration files. For example, you're looking for block H, and you try to open file block H, and this file is in two versions, one in temporary install and one in sources. Now I don't see it for some reason. Probably I had to ignore files. Okay, so what failed for us? What failed? A lot of fails in so small brief. Seems like most of fails are a result of us changing block size. Let's configure it back. Let's get back to 8 kilobytes and run make j8 install. The thing is, I'm having installation different from what was configured and compiled. This is important to run tests. You actually have to have an installation. Let's run check again. Something's wrong. Okay, something is wrong. Let's just configure with 8 kilobytes. And actually it was reporting to that checking 3 times or 4 times that the problem is in page sizes. Then you configure with 4 kilobytes something not working and configure with 8 kilobytes and everything is working. And after that, I think it was reporting to PGSQL generals or PGSQL hackers or other mailing lists. Now seems tests are passing. By the way, what is spgist? Spgist is a space partitioning generalized index search tree. So many words. This is simply one of geometrical indexes. Let's try to use it ourselves. It's necessary to define a benchmark for this patch. In Postgres, we can use geometrical types, for example, points. Let's create a table and call it X as select random point. Select point, both coordinates of which are random. Random from generate series, and say we need 1 million of these random points. Generate series. Yes, we need from 1 to 1 million. Yep, we got already 1 million of points. And then create index on X using spgist on column. Which column there? Column point. Okay. Actually, index is created in slightly bigger amount of time. And let's try to use it. Explain. Let's first select all rows where point is in a box from 1.1, 1.1 to point 1.2, 1.2. And this is a box column point. Yes, we see there is a 10,000 rows, and make sure that it was running through our index. Explain. We see that there was used index on the scan on our SPGist index that we have changed recently. Finally, let's format a patch. Git status. We see one file changed. See what's changed. We added some space error, so let's remove it. Where is it? Here we go. Some extra. No? No, I don't see it. Yeah, there they were. See git diff again. It's not that red now. And git commit everything. Typically, you write long commit messages explaining what's going on. Replace page add item with index tuple overwrite in SPGist. In fact, it's not enough for a proper patch. To make a patch for hackers, you should do all the same for Brin index and for hash index, and make sure it have no performance degradation. Git format patch version 1 and one file. Here we go. Here is our patch. Git checkout b SPGist overwrite and git push it to run CI tests. One final word about buffer pages. First, there is a page inspect. This is extension, Postgres extension, which allows you to get a page as a byte array from a relation and then deal with it with like breaking it in the items as byte arrays, and then deal with it as tuples and seeing what's there. And another interesting tool is PG Hex Editor by Peter Gagan and some other hackers. This is useful to inspect on-disk file to see which bytes are for. But to compile it, you will have to compile also WX Hex Editor and then use it on as an inspection tool, not to really write something into a database, but you can like see what these bytes actually mean. Okay, seems like that's it. That's all I wanted to show you today. Thank you so much for watching, and see you in further videos.